And we're back and better than ever in 18-3. In this podcast, we're going to be taking a look at the solubility product constant and talking about how little insoluble salts dissolve. So let's go ahead and jump in. The solubility product constant. Notice we're calling this KSP. K is the general term for any equilibrium constant. We're calling this KSP because it is the solubility product constant. And so there you go, as opposed to, say, KEQ, which, by the way, we typically drop the EQ for it. We just call it a K. But it's called KEQ because it's the equilibrium constant, and so that's just simply why we use that. Now, KSP. KSP is the equilibrium that exists between slightly soluble salts and the ions they produce in water. Now, we call them slightly soluble because they do dissolve to a small extent. If you think back to chemistry A, we generally call these insoluble because to the naked eye you can't tell that any dissolves. It's an incredibly small number, as you're going to see in just a second here. But let's take a look at one particular salt that we used before, silver chloride. Silver chloride actually is in a crystal of repeating silver ions and chloride ions, and it's going to look something like this. And this goes in 3 dimensions. This is not just a flat surface, but it goes back in 3 dimensions, forms a cube, and these cubes can go on, these ions can go on for literally billions and billions of units long. But what happens is that occasionally some of these ions get bumped off by the water molecules that this crystal is sitting in. But very, very quickly they get reattached. All right? And there's an equilibrium that exists where there's going to be small amounts of these ions floating around, but it is an incredibly small amount. That is the equilibrium that we're talking about. How much do these things get bumped off the crystal, and how quickly do they reattach themselves? And when that reaches equilibrium, where you have equal numbers bumping off and being reattached, how many of these guys do you actually have in solution? So let's go ahead and take a look at that. The letter A says to write the equilibrium expression for that following reaction. Well, we are dealing with a solid that's dissolving, so we're going to have KSP, the solubility product, and it's going to equal, in this case, both products, which is the silver ion times the chloride ion, raised to their coefficient's power. Well, in this case that's both 1, and then in the denominator you should have the silver chloride, but it's a solid, so it gets left off. As it turns out, every KSP, you're not going to have a denominator because you're always dealing with a solid that's dissolving, and since that solid gets left off or is turned into a 1, it's not going to be there. Next, in letter B, it says to determine the solubility product constant if both the silver and the chloride ions equals 1.34 times 10 to the negative 5 molar. So simply plug it in. You have KSP then is going to equal the silver, which is 1.34 times 10 to the negative 5 molar, times the chloride, which is also 1.34 times 10 to the negative 5 molar. And when you take those two quantities and multiply them, you do get 1.80 times 10 to the negative 10. And of course, there is no unit. Now for part C, determine the chloride ion concentration when silver ions equal 0.025 molar. You're going to be using the same equation, but now you know KSP, and they give you the silver. You just need to solve for this unknown. So if you want to set it up just so you can see what you're working with, KSP equals the silver ion concentration times the chloride ion concentration, and now plug in the values that you know. We know KSP is 1.80 times 10 to the negative 10. The silver is going to be 0.025 molar, and that's going to be multiplied by the chloride ion concentration. So to solve for chloride, simply divide over the 0.025. These terms divide out, and the chloride ion concentration is going to equal 1.8 times 10 to the negative 10 divided by 0.025, and it looks like it's going to be 7.2 times 10 to the negative 9, and we're dealing with concentration, so this is molar. So there you go. That would be the concentration of the chloride when the silver is 0.025 molar. Alright, let's go ahead and try another. Scrolling down, we're dealing with lead iodide, which is that bright yellow solid that gets formed. We'll go ahead and do this in green. The yellow won't show up. But the question is, again, write the equilibrium expression for the following reaction. So therefore, KSP will equal the lead concentration, lead ion, times the iodide ion concentration squared. Because you do have a 2 out front, you still have to raise them to their coefficients powers, and then nothing is in the denominator because that is a solid and it gets left off. Alright. Letter B, determine the solubility product constant if the lead concentration is such and such and the iodide is also given. So now we're just going to plug in those values where you have KSP equals 1.99 times 10 to the negative third times 3.98 times 10 to the negative third, and that value will be squared because the iodide is squared. And now when you evaluate that, you're going to be getting 3.15 times 10 to the negative 8. And again, no units on any equilibrium constant. Finally, part C. Determine the iodide concentration when the lead is 0.050 molar. You have KSP, which is going to equal your lead, 2 plus, times your iodide, which is squared. Plug in what you know. You have 3.15 times 10 to the negative 8, equaling 0.050 times the iodide squared. Divide the 0.050 over to the other side. And now the iodide squared is going to equal the 3.15 times 10 to the negative 8 divided by the 0.050. I'm getting 6.3 times 10 to the negative 7. And now you do have to look, this iodide is squared, so we're not done yet. We're going to have to raise both of these to the 1/2 power, or simply take the square root of both sides. And now, let's go ahead and finish the calculation up this way. The iodide concentration will equal the 6.3 times 10 to the negative 7 raised to the 1/2 power, so that will be, or again, square root, 7.94 times 10 to the negative 4. Now we're in concentration, and only concentration, so that will be molar. Alright, go ahead and try example number 4, dealing with aluminum hydroxide on your own. In the next podcast, we'll go ahead and go over that sample, and then we'll wrap up the chapter talking about the common ion effect. We'll see you next time.